Hello my friends and welcome back to the You Can Do TV channel. The steel recycling process begins with the collection of scrap metal. At here, the steel yard is designed to process and ship full truckloads of scrap metal. Inbound and outbound traffic is managed efficiently, with all vehicles reporting to the truck scale for weighing and inspection. The material is then unloaded and inspected for quality and grading. Obsolete metals, such as old appliances and bicycles, are processed through metal shredders that separate ferrous from non-ferrous materials. The non-ferrous products are further processed through separation systems to segregate different metal types. Once scrap metal is collected, it undergoes a sorting process to separate ferrous, iron-containing metals from non-ferrous metals. Ferrous metals, such as steel, are often shredded to break them down into smaller, more manageable pieces. This shredded metal is then processed through various separation systems that use magnets and other technologies to remove impurities and sort the metal by size and type. Non-ferrous metals, including aluminum, brass, and copper, are also sorted and processed separately. Steel is an ideal candidate for recycling because it can be repeatedly recycled without losing its properties, making it an excellent choice for businesses striving to reduce their carbon footprint. An arc furnace is an essential tool for melting and refining scrap steel into new steel using the principle of electric arc discharge to generate intense heat, exceeding 3,000 degrees Fahrenheit. The process begins with charging the arc furnace with iron and scrap steel, sourced from various industrial processes and recycled materials, making it an environmentally friendly choice. For instance, Metal Tech recycles millions of pounds of scrap metal annually using arc furnaces, reducing reliance on raw materials and promoting sustainability. Once the furnace is charged, a high-voltage electric arc produces intense heat, melting the scrap steel into a liquid state. As the steel reaches its molten state, the furnace becomes a refining vessel. During this stage, the operator controls the steel composition by adding refining agents and adjusting electrical parameters, removing impurities and ensuring the final steel product meets required specifications. Argon-oxygen decarburization, AOD, is a refining technique used to improve the physical properties of stainless steel and other ferrous alloys. The process begins with charging the AOD vessel, which is preheated and typically contains molten metal from an arc furnace, along with specific alloying elements and additives. Once the vessel is charged, a mixture of oxygen and argon gases is injected into the molten metal. The oxygen reacts with carbon in the steel, forming carbon monoxide, which is removed from the vessel, reducing the steel's carbon content. As decarburization takes place, alloying elements are added to achieve the desired chemical composition, improving properties such as corrosion resistance, strength, and heat resistance. The operator monitors and adjusts the alloy element levels to ensure the steel meets the required specifications. Once the desired composition is achieved, the AOD process is complete, and the steel is ready to be cast for its intended application. The 13,000-ton forging press, part of the facility's £400 million recapitalization project, will significantly enhance the company's defense critical assets. This press, the largest of its kind in the UK, offers unparalleled advantages in forging technology. Its immense capacity ensures the production of exceptionally large and complex components with superior precision and strength, vital for defense applications. The advanced automation and control systems integrated into the press will increase efficiency, reduce production times, and enhance safety. Raw metal billets are heated to a pliable state in a furnace. Once heated, These billets are placed into the press, where immense hydraulic force is applied, deforming the metal into the desired shape. The press utilizes advanced automation and control systems to ensure precise pressure and temperature regulation, crucial for achieving the correct metallurgical properties. The machine's sophisticated sensors and feedback mechanisms monitor the process in real time, adjusting parameters as needed to maintain optimal conditions. This ensures consistent quality and structural integrity of the forged components. The press can handle exceptionally large and complex parts, making it ideal for defense applications where precision and strength are paramount. The process begins with reheating the steel slabs in a furnace to temperatures around 1,100 degrees Celsius, 2,000 degrees Fahrenheit. Once heated, the slabs are passed through a series of rolling stands, where they are progressively reduced in thickness. Each rolling stand consists of powerful rollers that compress the steel, elongating it into a thinner sheet while simultaneously improving its grain structure and mechanical properties. As the steel passes through the rolling stands, it undergoes descaling to remove any surface oxides formed during heating. High-pressure water jets or mechanical scalers are typically used for this purpose. The continuous rolling process ensures uniform thickness and enhances the steel's ductility and toughness. ERW pile piles. The production of electric resistance welded ERW pipe piles begins with hot rolled coil steel, ensuring high quality from the start. The process starts with incoming steel coils being tested for tensile properties and yield strength to maintain flexibility and quality control. The coils are then slit to the required width according to the pile diameter to be produced in a given shift. Once slit, the coils are loaded onto the tube forming line. The steel is first uncoiled and flattened before being joined to the end of another coil through a butt weld. This welded joint is cut out and scrapped to maintain product integrity. The continuous steel sheet then enters the production process, where material tracking is maintained through permanent engraving of the heat number on the pipe's interior. This ensures full traceability of the steel source and manufacturing date, with an additional stencil applied to the exterior after the pipe is formed. To ensure efficiency, an accumulator stores up to 4 coils, preventing material lag during subsequent processing stages. The continuous coil of end-welded steel enters the spiral accumulator, allowing for seamless coil transitions without stopping production. The steel then moves through 5 forming rolls that gradually shape it into a U-profile, with each roll increasing the curvature until about 70% of the final shape is achieved. The rolling presses then switch from convex to concave, aligning and burnishing the strip edges in preparation for welding. The ERW welding process utilizes 2 copper contact shoes to pass an electric current through the strip edges, generating resistance heat up to 2,700 degrees Fahrenheit. This heat creates a longitudinal weld as the pipe moves at speeds of up to 120 feet per minute. Any excess material from the seam is removed using a scarf cutter, resulting in a smooth, nearly invisible weld. The pipe is then ironed while still hot to achieve the required diameter and dimensions for installation. Once welded, the pipe undergoes ultrasonic testing to verify weld integrity and detect any internal flaws. Defective sections are automatically removed, ensuring the highest quality standards. After testing, the pipe is gradually cooled using water and coolant to prevent thermal cracking. The Turk's heads then refine the pipe to its final size and provide a smooth surface finish. The last steps include external heat number stenciling, which corresponds to the initial internal ID stamp, ensuring full traceability. The cutoff saw moves in sync with the pipe to maintain continuous production, cutting the pile to the required length. 2 final destructive tests, cone testing and flattening, confirm weld strength and steel ductility. Each pile is then barcoded and accompanied by a mill test report, MTR, backed by Coil certificates from the steel supplier. With lengths available up to 125 feet, the finished Atlas pipe piles are shipped to stocking partners and project sites across North America and internationally, ensuring reliable deep foundation support for a range of infrastructure projects. A steel coil slitting line is an essential process in metalworking, particularly for preparing metal coils for subsequent manufacturing steps. Here's an overview of how a steel coil slitting line operates. The process begins with the loading of large steel coils onto the uncoiler. These coils are then fed into the slitting line, which is designed to cut the wide coils into narrower strips. This line achieves high output and flow rates by minimizing tooling times and maintaining high production speeds. High cutting accuracy is ensured through the use of precision knife shaft bearings. These bearings support the knife shafts and ensure that the slits are clean and precise, resulting in burr-less cuts. This is essential for maintaining the quality of the edges and preventing damage to the material. A critical feature of this slitting line is the movable braking unit, which allows for high winding accuracy even as the coil diameter increases. This unit ensures that the coils are wound tightly and evenly without the need for a separating system at the coiler, streamlining the process. Finally, the line is capable of processing materials with high strength, over 1,400 N per square millimeter, and yield points up to 1,000 N per square millimeter, making it suitable for a wide range of high-strength steels. Wusthof knives, renowned for their superior craftsmanship, are produced in Solingen, Germany using state-of-the-art facilities. Here is an overview of the knife manufacturing process: forging. The journey of a knife begins with the selection of high-quality chromium molybdenum vanadium steel. The stainless steel sheets are cut to size and heated to approximately 1,200 degrees Celsius, 2,200 degrees Fahrenheit. The knife bolster is precision forged in a die, providing the knife with its initial strength and form. Following this, the blade is cut from the forged piece with precision using a laser, giving the knife its basic shape. Tempering. The blades are heated to approximately 1,920 degrees Fahrenheit in a tempering oven, hardening them to a Rockwell hardness of 58. This ensures the blades are tough and durable. The blades are then rapidly cooled. To balance the hardness with flexibility, the blades undergo a secondary heating process in an annealing furnace at around 180 degrees Celsius. Grinding and polishing. The blades are then ground to refine their shape and smooth out any rough edges. Initially, the flat surfaces of the blades are coarsely ground by robots. Next, the blades are polished to attain a fine satin surface. The hollow edge of each blade is also sharpened by robots, ensuring precision. This grinding and polishing phase is critical as it defines the blade's sharpness and aesthetic appeal. Etching. The next step involves etching the blades. Each blade is closely inspected for quality before receiving the Wusthof seal of quality, which is the trident. The blades are electrolytically etched and then cleaned in ultrasonic units. Alternatively, they may be engraved by laser and imprinted in two colors. This process not only brands the knives but also enhances their visual appeal. Handle attachment. Handles are mounted automatically onto the knives. They are securely welded and attached to the tang using 3 rivets. The handle, bolster, and tang are polished by individually programmed robots with precision, ensuring consistency and the highest quality. Finishing of the handle. Although much of the process is automated, manual work remains essential for finishing the handle. The surface of the handle and the stainless steel rivets are polished to make them smooth. The surface is rubbed down, and any remaining edges are finished by skilled specialists. This manual intervention ensures that each knife has a perfect finish and is comfortable to hold. Sharpening. The final step is sharpening the blade to achieve ultimate sharpness. The facility employs a specially developed PC sharpening process. The blades are measured by sensors and lasers, and a computer program calculates the optimum angle for sharpening. The knives are honed and sharpened on a wet stone, and fine honing removes any remaining burrs. Each knife is then rigorously tested for sharpness to ensure it meets Wusthoff's high standards. The production of a Bach trumpet is a meticulous process that combines traditional craftsmanship with precise engineering. Each trumpet undergoes multiple stages to ensure the highest quality and best sound possible. The key steps in the production process are outlined below. Bell. The bell of a Bach trumpet starts as a flat sheet of brass. This sheet is shaped using a hydraulic forming process, known as hydroforming, which molds the metal into the desired shape. Once the initial shape is achieved, the bell undergoes an annealing process. Annealing involves heating the brass to a specific temperature to make it more malleable and easier to work with in subsequent steps. After annealing, the bell is further shaped through a secondary forming process to refine its contours. Next, the seam of the bell is meticulously aligned and brought together. Craftsmen carefully hammer the edges so that they meet perfectly, ensuring a strong and seamless connection. The bell is then run through a press to flatten the seam, making it smooth and virtually invisible. Following this, the bell undergoes a spinning process. An experienced technician, using a wooden tool, carefully shapes and thins the bell to achieve the precise dimensions required. The use of wood rather than metal minimizes stress on the brass. After spinning, any excess material is trimmed, and a brass ring is inserted and forced into place at the rim, reinforcing the bell's structure. Lead pipe. The lead pipe plays a crucial role in determining the trumpet's response and intonation. It is drawn from high-quality brass tubing, which is precision-formed to exact specifications. The lead pipe is then carefully cleaned and inspected for uniformity, ensuring that air can flow through it smoothly. Each lead pipe must be free from imperfections that could affect the instrument's sound. Valves and tuning slides. The valve assembly is one of the most intricate aspects of trumpet production. Each individual valve casing is constructed and fitted with precision-cut internal components. The valve ports are carefully aligned to allow for smooth airflow when the trumpet is played. Spacers and lead tubes are installed to hold the valves in place while ensuring the correct spacing between components. Once the valve casings are prepared, they are soldered into position. This requires expert craftsmanship, as even minor misalignments can affect playability. The valves are then honed to achieve an airtight fit. A similar process is followed for the tuning slides, which are designed to adjust the pitch of the instrument. These slides are drawn from brass tubing, shaped and polished to fit seamlessly into the trumpet's framework. Mouthpiece. The mouthpiece is an essential component that influences the tone and playability of the trumpet. Each mouthpiece is precisely machined from brass to ensure consistency in size and shape. The interior of the mouthpiece is carefully finished to remove any rough edges or imperfections that might interfere with sound production. Finally, the mouthpiece is polished to a smooth finish, ensuring comfort for the player. Putting it all together. Once all individual components are prepared, the trumpet is assembled. The bell is attached to the lead pipe, and the valve assembly is fitted into the instrument's body. Every connection is carefully soldered to ensure structural integrity and optimal resonance. After assembly, the trumpet is polished to enhance its appearance. The instrument then undergoes a washing process, with silver-plated models receiving a different treatment than lacquered ones. Lacquered trumpets are coated with a protective layer, while silver models undergo an electroplating process. Before leaving the factory, each trumpet is hand-fitted and adjusted by expert technicians to ensure that all parts function seamlessly. Any imperfections, such as small dents or alignment issues, are corrected before final testing. The trumpet is then play-tested by a professional to ensure it meets Bach's high standards. If any adjustments are needed, They are made before the instrument is deemed ready for sale. The global screws and nuts production industry is a vital segment of the fasteners market, which was valued at $93.2 billion in 2023 and is projected to grow at a CAGR of 4.5% from 2024 to 2030. This industry plays a crucial role in construction, automotive, aerospace, and industrial manufacturing. China dominates the sector, producing over 40% of the world's fasteners, followed by Germany, Japan, and the United States. The U.S. fastener market alone was valued at $15.2 billion in 2023, with automotive applications accounting for about 30% of demand. The European market is also significant, driven by high-quality precision fasteners used in aerospace and machinery. Steel, stainless steel, and aluminum are the primary materials used, with steel screws and nuts making up over 60% of total production. Innovations in high-strength alloys and anti-corrosion coatings are improving durability and performance. The automation of manufacturing processes, including CNC machining and cold forging, has increased efficiency, reducing production costs by up to 20%. Additionally, the push for sustainable manufacturing has led to a rise in recycled metal usage, now comprising 15 to 20% of raw materials in some regions. Asia-Pacific continues to lead the market growth, driven by rising infrastructure and industrialization, with India and Vietnam emerging as key players. In the ammunition production industry, specialized machines streamline manufacturing with impressive output. Shotgun shell loading machines can produce up to 10,000 shells per hour, while centerfire loading machines handle dual outputs for pistol calibers per stroke, achieving high efficiency. Primer inserting machines also reach 10,000 units hourly, ensuring rapid priming. Shot casting machines craft lead shot with precise sphericity, often exceeding 5,000 kilograms daily, depending on energy sources like natural gas. Lead wire extrusion machines transform billets into wire at synchronized rates, while buckshot machines support custom configurations. Bullet jacketing machines process complex assemblies, and double-action presses, resize machines, trimming machines, and grooving machines enhance precision, collectively yielding millions of rounds annually. Aluminum aerosol can lines consist of specialized machines that produce monoblock cans and bottles, commonly used for products like perfume, deodorant, hairspray, and paints. The fully automatic XR series includes key equipment such as an extrusion press, trimmer cum brushing machine, spray washing machine, internal lacquering machine, lacquer curing oven, base coating machine, 6 or 8 color printing machine, drying oven, and necking machine. These machines, controlled by Siemens PLCs, ensure stable, high-speed production, up to 120 pieces per minute. Gas-heated ovens reduce energy use, while branded components like NSK bearings and Festo pneumatics enhance reliability. A color touch screen displays real-time production data for efficient management. We're in Andritz Hydropower's factory that excels in the hydropower turbine production industry, leveraging 185 years of turbine design expertise. The company has manufactured over 33,200 turbines, delivering a global capacity of 489,000 megawatts. Its production spans small to large-scale hydropower systems, integrating advanced digital solutions and turbo generators, contributing to 16% of the world's hydropower-generated electricity. This axial closed die rolling machine is a specialized tool used in metalworking to form precise, seamless components like gears or flanges. It operates by rolling metal between rotating dies under high pressure, ensuring uniformity and strength in the final product. Betts Spring Manufacturing employs distinct processes for crafting springs. Cold winding begins with pre-tempered material, pulled through rollers and fulcrum pins, then coiled around a precision ground arbor, using high-tensile chrome silicon for lightweight springs with diameters from 1/8 to 5/8 inch. Hot winding heats bars to 1750 degrees Fahrenheit in a low-emission furnace, coils them around a mandrel, quenches them in oil, and tempers them, accommodating diameters from 1/2 to 1 3/4 of an inch for diverse applications. The production process of valves at a leading API-accredited manufacturing facility begins with sophisticated engineering design, utilizing advanced software and equipment to meet precise client specifications and international standards. Designs are transferred to an in-house pattern shop, where advanced CNC machines craft the patterns needed for casting. Casting and forging occur with various metals, including carbon steel, stainless steel, and titanium, tailored to valve types ranging from 1/2 inch to 56 inches. Heavy-duty CNC machines, such as vertical turret lathes and mega bore centers, handle machining, ensuring dimensional accuracy and superior surface finish. Pre-machined cast components are refined on these systems for precision. Welding stations employ techniques like SAW and GMAW for cladding and overlay, supported by robotic HVOF coating facilities to enhance corrosion resistance. Components then proceed to a dust-free assembly center, where trained technicians assemble valves under strict supervision, assigning unique serial numbers for traceability. Post-assembly, valves undergo extensive testing, high-pressure tests up to 20,000 psi, cryogenic tests to -196 degrees Celsius, and fire-safe evaluations, ensuring compliance with global standards before painting, packaging, and dispatch. At the CFF Vernayas power station, the stator reassembly process for Group 2 involved steps following the repair of the upper stator. Technicians carefully aligned and reinstalled the stator components within the generator housing, ensuring precise positioning for optimal performance. Rotating diodes were then integrated into the assembly, enhancing electrical efficiency. This process, part of a broader maintenance effort, was critical to restoring the unit's functionality, supporting the plant's role in powering Switzerland's electrified railway network with renewable energy. This CNC lathe operates by rotating a workpiece against precision cutting tools, shaping it into a desired form. An automatic bar feeder supplies raw material continuously, boosting efficiency by minimizing manual intervention. The dual turret design equips the machine with 2 tool holders, enabling simultaneous or sequential operations, reducing cycle times. Live tooling integrates milling and drilling capabilities directly onto the lathe, allowing complex features to be machined without repositioning the workpiece. In a twin spindle setup, 2 spindles work in tandem. One holds the workpiece while the other performs secondary operations, enhancing productivity. Combined with the horizontal boring mill, this configuration excels at handling intricate, large-scale parts with high precision. The production process of welded beams begins with raw flat steel plates, ranging from 10 to 40 millimeters thick, delivered via rail wagons. These plates are offloaded and cut to size using oxyacetylene flame planers. Next, the plates undergo blasting to remove rust, scale, and surface defects. 3 components, the web and 2 flanges, are then tack welded together at an assembly station, ensuring precise centering. Sub-arc welding follows, applying 4 8mm welds along the beam, first on one side, then the other. After welding, the beams are straightened if needed, cut to length, inspected, and dispatched directly to customers. Forging is a metal shaping process that involves heating a workpiece to a specific temperature and applying compressive forces to form the desired shape. This method enhances the strength and durability of the material by refining its internal grain structure. The process at this factory begins with selecting a suitable raw material, typically steel or alloy, which is cut into appropriate sizes using band saws or circular saws. The cut material is then heated in a furnace to temperatures between 550 degrees Celsius and 1250 degrees Celsius, depending on the material composition. Once heated, the workpiece is placed under a forging hammer or press. Smaller components are forged using steam hammers with weights ranging from 300 to 6,000 kilograms, while larger parts require hydraulic presses exerting forces up to 40,000 kilonewtons. Specialized manipulators ensure precise positioning during forging. Following forging, the components undergo heat treatment to optimize mechanical properties. Processes like quenching, tempering, and annealing improve hardness, toughness, and stress resistance. Machining and finishing processes refine the forged parts to exact specifications. Quality control measures, including ultrasonic testing and hardness testing, ensure compliance with international standards. Forged components are used in industries such as heavy machinery, aerospace, and energy due to their superior mechanical properties and structural integrity. Centrifugal casting is a process used to create cylindrical metal components by pouring molten metal into a rotating mold. The rotation creates a centrifugal force that distributes the molten metal against the mold walls, forming a dense and uniform casting. This technique is particularly effective for producing high-quality, seamless components with excellent mechanical properties. At Sandusky International in Sandusky, Ohio, the foundry department excels in producing some of the world's largest centrifugal castings, with lengths up to 36 feet and outer diameters up to 5 feet. These castings are critical components for various demanding markets, including defense, process industries, and the paper industry. The process begins with the careful positioning of centrifugal dies. These dies are large, precisely engineered molds that shape the molten metal as it is cast. Once the die is in position, the molten metal is poured in while the mold spins at high speeds. The centrifugal force pushes the metal outward, ensuring it fills every part of the mold uniformly. This method eliminates gas and shrinkage cavities, resulting in castings with superior structural integrity. Nathan Goebel, the general manager at Sandusky International, emphasizes the importance of their advanced capital equipment and skilled human capital. The manufacturing process of load hooks, critical components in lifting and rigging operations, combines time-tested forging techniques with modern technological advancements to ensure superior strength, durability, and precision. This process involves several stages: forging, heat treatment, machining, and rigorous quality control. Forging process. Forging is the foundational step in creating load hooks. Traditionally, forging involved heating metal billets to over 1,000 degrees Celsius, making the metal pliable. These heated billets are then placed between dies that shape the hook. Historically, forging hammers would strike the metal repeatedly with significant force, relying on the sheer energy of the hammer's fall to shape the metal. In contrast, modern forging techniques, like those employed by Rudd Schottler, use advanced linear drop forge hammers. Unlike conventional hammers, the linear hammer can precisely control its striking force, applying just enough energy to shape the metal without excess. This is achieved through a linear drive system that can stop the hammer within a few hundredths of a millimeter, resulting in highly accurate and finely crafted components with minimal material waste. Heat treatment. After forging, load hooks undergo heat treatment to enhance their mechanical properties. This process involves heating the hooks to a specific temperature followed by rapid cooling or quenching. Quenching alters the metal's microstructure, increasing its hardness and strength. Subsequently, the hooks are tempered by reheating them to a lower temperature and allowing them to cool slowly, reducing brittleness and improving toughness. Quality control. Quality control is paramount in the production of load hooks. Each hook is meticulously inspected to ensure it meets strict safety and performance standards. Visual inspections are conducted to check for surface defects, while non-destructive testing methods, such as magnetic particle inspection or ultrasonic testing, are used to detect internal flaws that might compromise the hook's integrity. Machining. Post-heat treatment, the load hooks are subjected to precision machining processes such as drilling, milling, and grinding. CNC machines are often employed to achieve high precision and repeatability in this stage. This step ensures the hooks meet the exact dimensions and surface finish required. If the design necessitates, threads are cut into the hooks for attachment to other components. Innovative forging technologies. Advancements in forging technology have significantly enhanced the manufacturing process of load hooks. For instance, the linear drop forge hammer, used by companies like Rudd Schottler, is a key innovation. Unlike traditional hydraulic hammers that require continuous maintenance of hydraulic oil, the linear hammer uses an electric drive system. Coils and magnets arranged around a steel cylinder produce a linear motion, allowing for precise control over the hammer's force and position. This precision results in less wear and tear on the dies, minimizing material waste and reducing energy consumption. The linear hammer only uses energy during the actual forging strikes, making it more energy efficient compared to hydraulic hammers that maintain constant pressure throughout the process. Benefits of advanced forging. The use of advanced forging technologies provides numerous benefits. The precision of the linear hammer ensures that each load hook is forged to exact specifications, reducing the need for extensive post-processing. This precision also means fewer internal defects, enhancing the overall strength and reliability of the hooks. Energy efficiency is another significant advantage. By eliminating the use of hydraulic oil and optimizing energy consumption, manufacturers can lower operational costs and reduce their environmental impact. The advanced forging process also allows for the production of smaller batch sizes economically, providing flexibility in manufacturing. Container manufacturing machinery encompasses a variety of specialized equipment designed to transform raw materials into finished containers, such as metal drums, cans, and large storage tanks. This machinery ensures precision, efficiency, and quality in the production process. Below is an overview of some essential machines used in container manufacturing. Shearing machine. Shearing machines are fundamental in the initial stages of container manufacturing. They cut large sheets of metal into smaller, more manageable pieces. These machines operate using a set of blades or rotary discs to perform straight cuts on the metal sheets. The shearing process must be precise to ensure that the subsequent forming processes proceed without issues. Skin pass roller machine. Skin pass roller machines, also known as temper mills, apply a slight reduction to the thickness of the metal sheets after rolling. This process improves the surface finish and mechanical properties of the sheets, making them more suitable for further processing and forming. Skin pass rolling enhances the flatness and uniformity of the sheets, which is essential for the subsequent manufacturing steps. Mechanical gut machine. Mechanical gut, grinding, outlining, and trimming. Spinning machine. Spinning machines are used in the forming of cylindrical and conical shapes from metal sheets. The process involves rotating the metal sheet on the lathe while applying force with a tool to shape it. Machines are used for precision grinding, shaping, and trimming of metal parts. In container manufacturing, these machines ensure that the edges and surfaces of the metal components are smooth and properly shaped. This is crucial for the assembly process, where precise fit and finish are required. This technique is particularly useful for producing parts like lids, bottoms, and other cylindrical components of containers. Spinning machines can be manual or CNC controlled, with the latter offering greater precision and efficiency. Hydraulic got machine. Hydraulic got machines perform similar functions to mechanical got machines but use hydraulic power to achieve higher forces and more precise control. These machines are capable of handling thicker and harder materials, making them suitable for heavy-duty container manufacturing tasks. Hydraulic deep draw press machine. Hydraulic deep draw press machines are essential for forming deep-drawn parts, such as large container bodies. This process involves placing a metal blank over a die and using a punch to draw the metal into the die cavity, creating a deep, hollow shape. Hydraulic deep draw presses provide the necessary force and control to produce complex shapes with high accuracy and repeatability. Buffing motor. Buffing motors are used to polish the surface of the metal containers, giving them a smooth and shiny finish. This step is crucial for both aesthetic and functional purposes, as a smooth surface helps prevent corrosion and makes the containers easier to clean. Buffing motors can be equipped with various types of buffing wheels and compounds to achieve the desired finish. Silver touch machine. Silver touch machines apply a protective and decorative silver coating to the surface of the containers. This process enhances the appearance of the containers and provides an additional layer of protection against corrosion and wear. The silver touch process is often used for containers that require a high-quality finish and appearance, such as those used in the food and beverage industry. The EV motor's stator production line is designed for high efficiency, precision, and reliability. It incorporates advanced automation and servo-controlled mechanisms to streamline the manufacturing process, ensuring superior quality and productivity. Universal movement stator stage. The stator production line is equipped with a universal movement stator stage, facilitating seamless handling and positioning of stators throughout the production cycle. This ensures smooth operation and minimizes errors during manufacturing. Servo-controlled paper feeding. To enhance insulation and durability, the system employs a servo-controlled paper feeding mechanism. This guarantees precise and consistent paper insertion into the stator slots, improving reliability and performance. The production line is designed for rapid delivery between stations, significantly reducing idle time and enhancing overall efficiency. This ensures a continuous and streamlined workflow. High-capacity winding. With up to 8 wires parallel winding capability, the production line accommodates high-density winding processes. The servo-controlled wire clamping system ensures precise control, preventing misalignment and maintaining uniformity. A turntable system with 2 working stations optimizes the winding process, allowing one station to prepare while the other completes its operation. 3-phase simultaneous insertion. The system incorporates a servo-controlled insertion mechanism capable of inserting 3 phases in one cycle. This significantly reduces the time required for coil insertion and ensures precise placement. Advanced tooling design. Professional and experienced tooling design enhances the adaptability of the production line. The tooling solutions are customized to accommodate various stator sizes and configurations. Vertical flip feeding for medium-large stators. For medium to large stators, vertical flip feeding is utilized to optimize material handling and reduce manual intervention. This mechanism ensures accurate positioning and smooth operation. Separated dimension forming. To maintain coil integrity and shape, the system employs separated dimension forming, preventing deformation and ensuring optimal electrical performance. User-friendly operation. Designed with an easy-to-operate, human-centered interface, the system allows operators to manage the production process with minimal effort and training. Pick-and-place function. An automated pick-and-place function streamlines component handling, minimizing human intervention and improving efficiency. Double-ended lacing for medium-large stators. For improved durability and stability, the production line features double-ended lacing, ensuring secure coil positioning in medium and large stators. Fully servo-controlled system. All critical functions, including insertion, forming, and wire handling, are servo-controlled. This ensures high precision, repeatability, and consistent quality. 3D forming design. A sophisticated 3D forming design enhances coil shaping and alignment, reducing material stress and improving longevity. The production line provides a complete turnkey solution for motor manufacturers, optimizing workflow, reducing labor dependency, and ensuring high production output. With its cutting-edge automation and intelligent control systems, the EV motor's stator production line significantly enhances productivity, reduces manual labor, and ensures superior product quality. The wind turbine tower production industry plays a crucial role in the global renewable energy sector, supporting the rapid expansion of wind power. The industry is driven by increasing investments in clean energy, government incentives, and advancements in wind turbine technology. As of 2023, the global wind turbine tower market was valued at approximately $28.5 billion and is expected to grow at a CAGR of 6.8% from 2024 to 2032. The demand is largely fueled by offshore and onshore wind energy projects, with offshore installations requiring taller and more robust towers. Leading manufacturers include Siemens Gamesa, Vestas, General Electric, GE, CS Wind, and Nordex. These companies operate large-scale production facilities in North America, Europe, and Asia Pacific. The average height of modern wind turbine towers ranges from 80 to 160 meters, with some offshore models exceeding 200 meters. Steel tubular towers dominate the market, accounting for over 85% of production, while hybrid and concrete towers are gaining traction for their cost-effectiveness and structural advantages. China leads in wind turbine tower production, manufacturing over 50% of global supply, thanks to its strong domestic market and cost-efficient manufacturing. The US and Europe also have significant production capabilities, with the US producing over 10,000 towers annually to meet domestic demand. India and Brazil are emerging as key players, increasing their production capacities to support local wind energy goals. During this virtual tour, we will look at the 5 major steps in the process of creating ductile iron pipe: melting, casting, annealing, lining and finishing, and quality control. Melting. The melting process includes the conversion of reprocessed steel scrap into a base iron suitable for pipe production. We begin with raw materials, mainly scrap metal, primarily from shredded automobile bodies. The scrap is melted in a tall cylindrical furnace called a cupola, which uses coke as a fuel source and small amounts of limestone to help remove slag from the liquid iron. Preheated air is continuously blown into the coke bed at the base of the cupola to generate the high temperatures needed to melt the steel scrap. As the molten iron exits the cupola, lighter impurities rise to the top and are skimmed off. The molten iron is then moved to a large ladle, where sulfur is removed by adding lime. After sulfur removal, the iron flows into a large holding vessel called a forehearth. Casting. Once the molten iron is treated and ready, it is transferred into smaller pouring ladles that hold enough molten iron to produce several pipes before needing a refill. The treated iron, containing a balanced composition of low sulfur and magnesium, is essential for achieving the desired ductile properties in the final product. Mold and sand core. The casting machine operator begins by placing a sand head core into the bell end of the steel mold. These sand cores, formed from sand bonded with resin, are critical in shaping the bell and gasket seating area of the pipe socket. The sand cores are produced in a machine similar to a large waffle iron, where they are heated to set and harden. Pouring and spinning. The actual casting starts when the operator tilts the pouring ladle, allowing molten iron to flow down a chute into the mold. As the iron fills the mold, the operator moves the mold assembly along the machine bed on rails. The mold rotates horizontally at high speeds, creating centrifugal force that pushes the molten iron against the mold walls, ensuring uniform thickness and forming the pipe barrel. This process typically takes 30 to 90 seconds, depending on the pipe size and class. Peening and solidification. The mold's inner surface features a bumpy pattern known as peening, which helps the liquid iron adhere to the mold walls, preventing splashing and ensuring a defect-free cast. The centrifugal force also acts as a self-cleansing mechanism, forcing impurities like slag and gas to the inner surface of the pipe, where they have no detrimental effect. Cooling and extraction. After the iron solidifies, the sand core is broken up, and the finished pipe is extracted using a pipe puller mechanism. The hot pipe is placed on rotating rollers to maintain its roundness and straightness before moving on to the annealing process. Annealing. The hot pipe is placed on rotating rollers to maintain roundness and straightness before being placed in the annealing oven. Annealing is a heat treatment process that produces the desired mechanical properties of the ductile iron pipe. This takes place in a natural gas-fired oven where the temperature gradually decreases as the pipe moves through the oven. The annealing cycle takes about 35 to 45 minutes. Prior to annealing, the pipe is fairly brittle due to rapid cooling during casting. The annealing process ensures the pipe has the correct properties and does not crack easily. Quality control. Quality control measures are in place throughout the manufacturing process. From the melting lab to the final product, samples are continuously analyzed for correct properties. Each stage of the process is monitored, and personnel have access to information through computer workstations. Special attention is given to possible detrimental elements such as tin, copper, and chrome. After the annealing process, each piece of pipe undergoes extensive inspection and testing. If any pipe fails to meet standards, it may be reworked or scrapped. Lining and finishing. Once annealed, the pipe undergoes extensive inspection and testing. After cooling, Each pipe is inspected for visual defects and gauged for proper dimensions. The pipe is also weighed to ensure it meets minimum weight standards. Following weighing, the pipe is bar-coded with information regarding weight and class. The pipe then undergoes a water pressure test, and samples are taken to determine mechanical properties such as tensile strength, yield strength, elongation, and impact strength. Final inspection and shipping. After passing quality control, the pipe is marked with information such as the class of pipe, date of casting, and additional details. The pipe then moves to the finishing area, where it is lined with cement mortar and coated with asphalt. The cement lining process involves rotating the pipe and using centrifugal force to apply the cement to the wall of the pipe. This helps prevent the buildup of corrosive products on the pipe walls. After lining, the pipe is allowed to cure for at least 24 hours. Finally, before loading for shipment, each piece undergoes a final visual inspection to ensure the seal coat is properly set. These cases house gears and bearings, requiring precise tolerances for optimal performance. Machining involves milling, drilling, and turning to restore or create accurate surfaces. Line boring ensures perfect alignment of bearing bores, minimizing wear and increasing efficiency. Specialized equipment like portable line boring machines and CNC mills are used for in-situ repairs, reducing downtime.